All right, so the CBC with Diff, CBC with Differential. So when you order a CBC, it can be without Diff or with Diff, and that can be with Diff, with manual Diff, or with automatic Diff. So the manual Diff means you want to wake up a phlebotomist, or not phlebotomist, but a lab specialist at 3 in the morning, and they're going. They're going to actually count the cells and tell you what they look like, tell you if they see schistocytes, see if they have all these different things. Whereas the auto Diff is the computer's doing it, right? So there's a difference, and when they're really looking at more specifics, like a hematologist needs to be consulted, that's usually when they're doing the manual Diff, right? So CBC with Diff, whether it be auto or manual. So what are you looking at here? We're looking really for white blood cells. Will you get the MCV, MCH, MCHC, all these other fun stuff? You will. But we're really looking at the stuff in yellow now, right? So we get a white blood cell count, right? And that's 4 to 12K, 4 to 10K. That's our normal white blood cell. But now we're looking at the other pieces, right? What is the mnemonic? It's NLMEB, never let monkeys eat bananas, right? So no, right? So no, never, it's like Wu Pang. It's like never, no, stop it, right? So never let monkeys eat bananas. So in neutrophils, those are in the highest amount. And the nice thing is that this mnemonic also is equivalent to the percentage of what it should be, right? So average neutrophils are 60 to 80%, so never 60. L, lymphocytes, 30, right? M, monocytes, 6, 3, 1. So that's the usual percentage of our white blood cells on differential, right? Because if you add all those up, it should equal 99% or 100%, right? So that is 100% of white blood cells. So we take the neutrophils are about 60% of our blood cells. Our white blood cell count is 10,000. 6,000 of those are neutrophils, right? That are floating around in the bloodstream, doing their thing. And what is their thing? To attack things, and they definitely rise with bacterial infections, right? They rise with viral infections also, but it's bacteria is really where it's at, okay? What about lymphocytes? Lymphocytes, those are your, they live in the lymph nodes, right? And those are where your B cells and T cells are at, right? So your B cells and T cells are lymphocytes, and that's your next biggest percentage of white blood cells, right? And what do B cells and T cells do? We'll talk about those in more detail, but B cells are releasing antibodies, or our T cells are really kind of running the show. They're like the commander-in-chiefs. Also, they have like little bounty hunters that are attached to them that are actually going out and specifically, smartly, CIA-like and FBI-like, trying to find the pathogen. Okay, monocytes, those are our baseline warriors, our frontline men. Those guys are just stationed already in different parts of the world, different parts of the body. The liver as Kupffer cells, the skin as Langerhans cells, the brain as microglia. They're staffed everywhere, right? And also you have some that are floating in the bloodstream, because you could have bacteria that bypass the liver or bypass the normal routes. And then we have eosinophils and basophils. So eosinophils will go up in an allergic reaction. That's usually the use for the eosinophils. Basophils aren't as useful. You're usually looking more at history more than anything else for basophils. Right, yes, they do viral more than bacterial, but you're also going to have viral with neutrophils. So like how are you going to tell which one's which? Okay, but eosinophils, though, those 100% go up with allergic reactions. Someone has a allergy to penicillin, for instance, and there's then you can look at their white blood cell right after. You're going to see the eosinophils be ridiculously high, more than what percentage?
More than 60%.
Just run it through. 60, 30, 6, more than 3%, right, would be a allergic reaction. Okay, and then we have a division of our neutrophils. So our neutrophils, there's old ones, and we can bring in new guys into the party, and those are called bands. So bands are neutrophils, and those go up with infection or with a neutrophilia, with increased neutrophils, right? As we use up our neutrophils, we're to get young, in quotes, neutrophils, but those are called bands. So we'll explain why they're called bands, right? So there's all kinds of differentials you can do. Basically, you just got to get the regular, just to make sure I got the never let monkeys eat bananas on my differential. And if you can throw bands in there too, cool, right? That's what's going to be on your differential. Okay, and we talk about the reasons why your white blood cell count will go up, but now we're kind of talking to different pieces of the puzzle here.
Do you have to add that on if you order it, or it's just a CBC with Diff?
So CBC with Diff should capture your bands as well. If it doesn't, we have to then add it on as a band count. Okay, so CBC with Diff, normal. WBC differentiation. So we talked about this in the opening, right? So N was 60% or your neutrophils, and that's a combo of your bands and neutrophils, right? So bands are neutrophils. They're going to be it eventually once they reach 21. I don't know, 20 years old. I don't know. So you have a neutrophils and bands, and sometimes your CBC on the computer, especially our computer, doesn't tell you that they're both neutrophils. You just have to know that neutrophils can be segmented, or they can be non-segmented, or they could be bands or segs, or they could be polymorphonuclear or non-polymorphonuclear or monomorphonuclear. So it's like, and then they just hope that you know which one's which. So that 60% is a combination of both. Normal bands are maybe about 3%, 6% in there, right? That's a normal percentage of your neutrophils. So 60% is the total, 54% is neutrophils, the other 6% are your actual bands. So it's a smaller division of your neutrophils. So we got segmented and non-segmented. We kind of touched on that. Our neutrophils, usually that's only one nucleus. That's a huge nucleus. That's been, again, like I said, like your favorite pillow from when you're a kid, or your favorite snake, I don't know, favorite snake stuffed animal. I don't know if people snake stuffed animals are a thing, but you have then it's going to get really lopsided and really, it's all one thing, but it's bulbous on different sides, right? So we have a bulbous mononuclear, but it has all kinds of different bulbs to it. So they call it polymorphonuclear, right? So it's one nucleus, but it's really bulbous in shape. Whereas the young ones, they are smooth. So they have a smooth nucleus. They call them bands for that reason, just like a little band nucleus, instead of being polymorphonuclear like this one, right? So here's neutrophil. You can see how it just lights up compared to the other ones, right? And the other ones get their name because of how they stain in the lab. So there really is no other trick to it. So what else? You got immature white blood cells. Those are our bands, right, which are non-segmented neutrophils. And we have our mature white blood cells. Those are your never let monkeys eat bananas. Neutrophils are in there. And monocytes technically are younger versions, because monocytes will grow up to become what? Monocytes grow up to become, that should be macrophage. So macrophage, right? Macrophage are the ones that are circulating around the bloodstream, and also they're going to be going into tissues and doing their thing. Okay, so those are your macrophages and monocytes. Monocytes being a younger version. And then what else? Where do we make all this stuff? Where is all this stuff happening? The stem cells are in the bone marrow, right? The stem cell is going to divide when it's stimulated. So when it's stimulated by EPO, it's going to make what? RBCs, right? So RBCs are made when we have EPO. So when EPO is around, stem cells, okay, I guess I'll make more RBCs now. When TPO is around, what gets made? Our platelets, right? So you got EPO, TPO, and then what stimulates white blood cells? Well, that's all these other tiny little chemicals, right? Interleukins and chemotaxins and other fun stuff and cytokines that are going to stimulate white blood cells to differentiate into their respective parts, right? Whether it be neutrophils, lymphocytes, monocytes, basophils, or eosinophils, right? So our diff has our different counts there. And then, again, we talked about the ones that are witness protection over here. Those are your ones that are undercover. Your monocytes have many different names, right? Depending on where they're at, where they've specialized. Whether they be microglia in the brain, they be liver cells are Kupffer cells, liver monocytes are Kupffer cells, Langerhans are in the skin, etc. Okay, and then lymph nodes. In lymph nodes is where your lymphocytes hang out. That makes sense. That's how they got their name. And we have two types of lymphocytes, and those are your B cells and T cells, right? And we'll talk about those coming up. And then the spleen is the biggest lymph organ you ever saw. It's something you can palpate on someone who's thin. You can blot it. You can actually, it's a huge Brita filter for your whole body, and all the blood goes through it. And it makes sense that you want all the blood to go through it, because if something is a pathogen in your blood, you want it to eventually get detected. So you don't want to get detected by these little monocytes and macrophages that are floating around. You want it to actually get filtered through this huge lymph node, and they're going to filter every single, like a customs check at an airport, and they're going to make sure that everybody has their ID. Okay? If they don't have the ID, which is your antigen, that's going to be a reason for them to flag them, and they're going to then mount an immune response against it, right? And then we have the thymus. The thymus is a blood cell organ you could think of. It's a white blood cell organ. It's a thymus is the only organ that disappears over lifetime, besides maybe your adenoids, right? Where are your adenoids at? Good. All right. So you have your adenoids and you have your thymus. They involute. They don't evolve or evolute. They involute over time. So usually by age 18, 21, your thymus is gone. It's done. Right? The organ is no more. It's like if your heart were to involute. It's like, at age 70, my heart's gone. Right? So it's like, well, my heart was gone at 25. I'm kidding. So you have a involution of this organ. Okay, and that's going to cause that's where my T cells are going to grow up. It's a university for your white blood cells. Only one specific white blood cell, and that's your T cell. Your T cell goes for your T organ, your thymus, right? Not your thyroid, but your thymus, right? And so it's literally a university. It has all the encyclopedic information of all the antigens that are out there. So all the antigens and pathological antigens, the ones that we have, the ones that are foreign, not foreign, so that when it works for TSA later, and it has a very joy-filled life as a TSA agent, it's going to then be able to recognize what is self and non-self, right? What is so it doesn't develop an autoimmune condition, but also so you like myasthenia gravis and Guillain-Barré is prominent in those who don't have a thymus, right? That could be the reason, or it's going to let you know what to make in case you see an antigen you're familiar with, right? And we'll talk about what you make. You make a antibody against antigens, right? So you have an antigen, and then your cells out there in the periphery, they're like, oh, look at this, look what I found, and they present that to B cell and T cell, and the T cell puts on his little glasses like a wizard. It's like, oh, I've seen this before, and it goes to its library, it opens it up and says, okay, we're going to make this antibody against that antigen, right? Because antibodies are specifically designed like a Lego set. They go exactly to the antigen in question. If they don't, you could start attacking yourself, right? Like glomerulonephritis happens when you form antibodies against strep of the strep throat. And then those antibodies you form against strep also look exactly like a podocyte in the glomerulus. So you get glomerulonephritis as well, or post-streptococcus group A beta hemolytic strep, right? So that's something that can happen if we are not careful, right? So that's the idea behind the thymus and the T cells, right? But our B cells are the ones that are going to eventually make all of our antibodies and are going to help mount the immune response, okay? So that's our thymus, and then we have mast cells. Mast cells are ones that are usually are prominent in anaphylaxis, prominent in allergies. They have some utility. Mast cells are like a glass castle of white blood cells. So whenever they get attacked by an antigen, all they do is they react like an ostrich. Like they stick their head into the ground, and then they self-detonate, and then they explode all of their contents, and then that activates an immune response, right? So mast cells are also involved in an immune response. So hematopoiesis. So hematopoiesis is how do we stimulate the white blood cells all the way at the top over here? How do we make all this stuff happen? It's a whole domino effect that's going to occur when we are in response, when we get a call to make our RBCs, right? It's like, send a raven, we need to make more RBCs, right? It's like, oh, we need more platelets, send thrombopoietin. And then when you need more white blood cells, what do? It's usually in response to like an immune response or in response to an SNS response. This is going to trigger the white blood cell cascade to start firing off. You can see this is why hematology is ridiculous. They don't name this something useful. They don't call it erythropoietin. Like they fired that guy in the 70s, right? It's like, why did you make it sound like something that students could actually learn one day, right? They said, no, listen here. It's IL-1, IL-6, IL-7, SCF, IL-11, IL-12, LHF, GCSF, right? That's hematology. There's literally like 80 of these chemicals, right? So it's ridiculous. So they have all these different chemicals that are going to trigger from one thing to the next thing, and from that thing to the next thing, okay? So you have cytokines, which are like interleukins are examples of cytokines that come from white blood cells. These are interleukins. They are little ravens between white blood cells, right? Between little colonies that are literally stationed up in the bone marrow. They tell, hey, we need more B cells. Hey, we need more T cells. Or hey, we need more monocytes. Or we need more neutrophils. Or bands, it's your turn. It's turn to go into the fight now. So those are different interleukins that get released from your white blood cells. There are other cytokines that get released, like your adipose tissue also releases these interleukins, and interleukins are inflammatory. And we know if we have chronic inflammation, that leads to problems. Like obesity has chronic inflammation, leading to to insulin resistance, for instance, in type 2 diabetics, or leading to rheumatoid arthritis, leading to osteoarthritis, leading to chronic kidney disease, and ASCVD, and all these other problems that can happen with our with adipose situation, right? Osteocytes, you get myocytes, all these things are going to release all these chemicals that are going to cause an immune response. We do want an immune response when we have a pathogen that has presented itself, right? When there's some kind of pathogen that's going to be presented, right? And how do we know we have a pathogen? Well, its antigen could just make its way into the bloodstream. That could happen. Or the bacteria could just be walking the wrong street at night. Or we have different cells in our immune system that are going to respond to the antigen, right? And they're going to release, hey, I see something, and they're going to release all these chemicals in the bloodstream, and they're going to cause this immune response to initiate. Okay, so we have interleukins, we have interferons that get flown around. We got ferritin. When we talk about ferritin with iron, it's like, what does that have to do? It's like, well, if I have an immune response, I probably need more oxygen, so I'm probably going to get more ferritin, which are Ubers, to get iron mobilized to the blood marrow, to the bone marrow, so I can make more RBCs, right? So ferritin is something you can actually measure on someone who has an inflammatory process. So like back in COVID times, like, do you have COVID or not? They ran a ferritin level, and they said, oh, you have an immune response mounted, so you probably have an acute infection. Okay, and then procalcitonin. It only rises with bacteria, but when you have any kind of bacterial pathogen make its way in your bloodstream, procalcitonin gets made immediately. It's an acute phase reactant. It's something that gets made when you have bacteria around, not with viruses, but because viruses actually inhibit this process. Okay, so the other system that gets fired off when you have an immune response is the complement system, right? So the complement system here are different proteins, and then again, it was named, it was named by a hematologist if they have, it's like C4, C6, C12, C36, C3A, C5, C5A, right? So come on, why don't you just name it what it does and how it works, and then we can figure it out. Like when I learned about the RAS system, I got renin, and I got angiotensin 1, first angiotensinogen to angiotensin, right? So it's like, that makes sense. Like a gen, and then I take the gen off, that makes sense. Like, so this wasn't designed by a cardiologist, it was designed by a hematologist. If they got their way, they would have turned these into Roman numerals. I guarantee it, right? And then you got this one guy who has a computer science degree. He's like, no, let's make it binary. That'd be cool. It'd be C100111100. It's like then they'd have their day, right? Then they like high five each other at the next conference. So yeah, so that's the complement system. What does the complement system do? It ultimately causes opsonization. Opsonization is opsonizing something. It's like optioning something. When you option something at an auction, you flagged it, right? So it flags it, it lights it up for the immune system to then see it. So now it sees the pathogen, and now it's lit up, and now it can start attacking it with our own defenses, right? So it opsonizes it. It also releases some chemicals that will actually perforate the pathogens as well, the bacteria. So there's benefits of the complement system. So opsonizes, it's going to recruit with chemotaxins. So it releases all these different things. So it's like it brings all the boys to the yard. It's going to release all these little chemotax, little milkshakes, like, and then it's going to bring all these people are going to come out, and those people are our white blood cells. It's part of the process that's going to get this immune response mounted, right? So it degrades mast cells, little glass castles or glass houses. Those guys get degraded, and they're going to release their process, and their process is going to cause an immune response in of itself. Okay, so all of this is what mounts the white blood cells. Yes.
So can you explain the role of procalcitonin?
So procalcitonin doesn't have any role. It just gets made, and someone said that's cool, right? And obviously wasn't named by a hematologist. It was like procalcitonin was it's like, oh cool, that's neat. It was named by an endocrinologist. An endocrine is much easier to understand, ironically, because you actually have names for things and things make sense. But yeah, procalcitonin is just something that they found. Hey, with bacterial infections, this procalcitonin is elevated, right? It's something we noticed the last 15, 20 years.
And it's not that it's like, because our computer will show elevated at like 0.2, but it's not indicative of bacterial infection until 0.5.
Usually 0.2 technically, yes, but if they have like renal insufficiency, you're gonna have more procalcitonin just circulating baseline. But yeah, if it's definitely more than 0.5, you're concerned. Like a renal patient, maybe 1. But yeah, when your procal is elevated, it's a bacterial infection. like the end of story. You can't. There's nothing else that makes procalcitonin happen like that. Okay, there are some rare things, but it's like that's not for 99% of the population. That's what's going to cause it to be elevated. Okay, so we mounted the immune response. How do we maintain it, right? So you cause all this action to happen. How do you maintain it? Well, we cause a lot of things to get fired off down here, and especially this guy right here. This guy is our CD4 cell. It's like, come on, hematology, right? It's our helper T cell. They're like, and they fired that guy also, right? Because the helper T cell helps out the whole immune response. It's going to release its own chemotaxins. It's going to tell all the cell lines to start dividing and doing their thing. And those guys release their chemotaxins, their interleukins, their interferons, and they're going to cause more T cells to happen. And it's going to be over and over and over. It's going to mount the whole response, right? And then, as we know, HIV knocks this guy out. That's why they're so immunocompromised.